Okay, so today's topic is going to be Unit 2.1, and this is Day 8, and this is going to be Part A, and this is just simplifying radicals. So we're going to split this up into a couple different sections here so that we can do one part so that we can, more effectively do the next one. And before we get started, our objective is to simplify radicals using what we call perfect square factors. And so this is what we're going to look at today. We're going to look at this idea of perfect square factors. And then what I have written here, something that I would like you to copy down, are these perfect squares. So the idea is we're looking for these square factors that will simplify down to something else. So for example, the factors that we're going to be using are actually the square roots themselves, not the numbers that they're equal to. So for example, we have a perfect square factor of 1, 4, 9, 16, 25, 36, 49, 64, and 81. Those are some of the most common perfect square factors that we're going to be using to be able to simplify our radicals. So before we get into anything else, we just need to make sure that we have a couple of vocab words that are kind of on par with what we're trying to look for and what we're trying to do. So when we talk about simplifying, we can look at things like using our order of operations, or PEMDAS, combining like terms and anything that's associated with that, or even as far as reducing fractions. But what this is also going to mean is removing what we would consider would be removing all perfect square factors from what we call radicals. Now, radicals are basically just another name for a square root. So whenever we refer to radicals, we're really just referring to square roots. Now the next part is what we call a radicand. Now the radicand is a little bit different, but the radicand is what's inside. So whenever we refer to a radical, that's the whole thing. The radicand is what's inside. So the idea is that what we're trying to do is we're trying to simplify these radicals by finding perfect square factors inside the radicand. Now perfect square factors are just like other factors that we've been using. So for example, if I was to take the number 16, obviously the idea is that we can find factors of 16, but what we're looking for is we're looking for the perfect squares that are involved with that. So we have 1, 2, 4, 8, and 16 are all the factors of 16, but what we're looking for, we're looking for those perfect squares that we saw on that other page. So 1, 4, and 16 are all perfect squares that divide into 16. So it's just like finding factors, but we're looking for specific factors. And that's what we would call our perfect square factors, because those are the things that we can take the square root of and actually find the value very easily. So all this referencing to not simplified fractions or simplifying radicals, what does that look like? So for example, what we have here is we have some examples and we have some non-examples. So we have non-simplified radicals over here, and then we have their equivalent radicals on the other side. So the square root of 8 would become simplified 2 times the square root of 2. It's not that it's on the outside, it's just that it's multiplied, so it's 2 times the square root of 2. The square root of 16 can be simplified to just 4. We would never leave a perfect square like this. As a radical, we would write it as 4. The square root of 28 will somehow simplify to 2 times the square root of 7. And then the square root of 75 will reduce to 5 square roots of 3. Now these are the same thing, so if you were to put these in a calculator and you would plug these in, you would get the same answer. But the idea is that this is the simplified answers that we're looking for, and this is how we want to write all our radicals. Again, this kind of goes back to writing exact answers. So whenever we're looking for things, we want their exact answer and not their approximate value. So instead of writing it this, which could be a lot of things, we're just going to write it as his exact answer, 2 square roots of 7, and then we can manipulate that and we could actually simplify that even further if we had something specific. Okay, so now we're going to get on to actually simplifying these radicals. And so here's our example here. We have the square root of 32, and what we're going to do is we're going to find the largest perfect square factor that will divide into the radicand. And for your convenience here, what I've done is I've written these perfect squares that we're going to be looking for. So these values down here are the values that we're going to try to divide into. Now obviously factors can't be any larger than the number itself, so we can kind of cut that off and only look at these particular values right here. Now we're going to eliminate 1 because 1 isn't very useful to us. Even though it's still a perfect square, it's not going to be very useful. So we need to figure out if 4, 9, 16, or 25 will divide into 32. Now again, what we're looking for is we're looking for the largest perfect square. So 4 does work, 9 doesn't work, and 25 doesn't work. So we're left with 4, and then we're also left with 16. But the idea is that we're still trying to find that idea of the greatest common factor, that kind of thing. And so what we're going to do here is that we're going to use 16. 16 is the largest perfect square factor that goes into 32. And so the second thing that we're going to do is we're going to separate these. So how I separate these is as follows. So I'm going to rewrite 32 as a number with a factor of 16. So what that becomes is that becomes the square root of 16 times by 2, because 16 times 2 gives us 32. So we're writing those factors out kind of in the same way that we did the a times c kind of thing. But the idea is that we're writing those separately. Now what I can do with these is I can separate these into their own square roots. So the square root of 16 and the square root of 2. So the whole idea is that we can separate those perfect squares from the regular factors. So we can kind of give them their own square root. So the square root of 32 factors to 16 times 2, which then separates to the square root of 16 times the square root of 2. Now here's where the perfect square comes in. The square root of 16, I know what that is, which is just 4. And then since the square root of 2 is not perfect, I just leave it as it is, and so it's 4 times the square root of 2. And so that's the square root of 32 simplified. So I'm finding those perfect square factors, taking those out, finding the square root of those, and then just rewriting as a simplified radical. So let's look a little bit further here. So again, we're using 1, 4, 9, 16, 25, 36, and 49, and 64, and we can kind of keep going, but obviously we're not going to use any of those too large of values. Again, I'm going to get rid of 1 because I don't really need that. So I'm looking for those perfect squares that will divide into 72. Now, this can be done in a couple different ways, but we always want to look for that largest value. But the idea here is that the square root of 72 can be rewritten as 36 times 2. So I can see right away that 36 goes into that. Now, it's not wrong to say that 4 or 9 will also go into those values, but again, we're looking for the largest perfect square. Now that I have my two factors, I can separate them apart. So the square root of 36 times the square root of 2. We know the square root of 36, which is just 6. Since we don't know the square root of 2, we just leave it as the square root of 2, and so my simplified answer is 6 square roots of 2. Okay, my next answer, or my next problem is very similar to that. So I have the square root of 12, so I find the perfect square factor that would go into 12. There's really not a whole lot of options there. It's either 4 or 9, and 9 doesn't go into 12. So my two factors would be 4 times 3. Now I can go ahead and separate those. The square root of 4 times the square root of 3. I know the square root of 4, which is 2. So the square root of 4 is 2 times the square root of 3, and now I have my simplified radical. Keeping going, the square root of 50 simplifies to 25 times 2, always looking for that largest perfect square. I'm not looking for, again, I'm not looking for any factors. I'm looking for only perfect squares. So some of you might try to do 5 times 10. Neither one of those are perfect squares, so we're only looking for perfect squares. So square root of 25 times 2 becomes the square root of 25 times the square root of 2. The square root of 25 becomes 5 square roots of 2. And so there I have simplified radicals. And the last one, we have 18. So that's the square root of 9 times 2. So the square root of 9 times the square root of 2, which simplifies to 3 square roots of 2. So again, in order to simplify radicals, all that we're looking for is we're looking for those perfect squares. We kind of remove those perfect squares, and they kind of go out into the front. And so that's the idea of simplifying it, so that this number inside is as low as possible and doesn't have any other perfect squares that divide into it. Now we can do this in a couple of steps. So for example, I could have done 72 in a couple of different steps. So the square root of 72, let's just say the only value that I could think of right away would be 9. And so I would write this as 9 times 8. And so when I look at this, 9 times 8, that's still that's one perfect square. And so the square root of 9 is 3 times the square root of 8, which is left over. But then I would have to reevaluate this and say, okay, are there any perfect squares that go into 8? And then I can start that process all over again. So I would have 3 still times the square root of 4 times 2, because I can separate those, and then I can keep going with that. So I'm still separating this, I'm still working with it. So 3 times the square root of 4 times the square root of 2, they're all being multiplied together, so it's no different than kind of our commutative associative properties here. They're still kind of all being grouped together. And so from that, I can get 3 times the square root of 4, which is 2, times the square root of 2. And then I can just multiply those two numbers out in the front, which is 6 times the square root of 2, and go figure, that's the same answer that I got over here. So it doesn't really matter how I do that, as long as I keep finding those perfect squares, removing them and separating them, and then just multiplying them at the very end. And so that's going to do it for this particular video on how to simplify radicals.